Section 7.3 is volumes. So the first thing we want to do is a quick review of volumes of various plane regions. So a square with a side length x, the area is x squared. Go through the others, see if you can come up with areas, pause the video, and then we'll check them together. Okay, these are the solutions you should have gotten. If any of these are ones you're not familiar with, I'm thinking particularly the bottom two, we will talk about those when we get together. But these are areas of plane figures that you should know. So the volume of a solid, when we take cross sections, remember when we have a plane figure, something like this, and we do little sections, that's rectangles. If we have a solid that we want to get an integral for, then each cross section is a plane figure, and so we need the area of that figure to do our integral. So this is going to be the area of the plane figure. dx is the width of each figure. That gives us our volumes that we are adding up. And as this dx approaches 0, we end up with an integral from some number to another of that plane surface area times its width, which gives us a volume. So our method is going to be, first of all, sketch the solid and find its typical cross section, find a formula for the area of that cross section. By integrating, we then will be able to find our volume. So the first one we're going to look at is a pyramid 3 meters high, has congruent triangular sides, and a square base that is 3 meters on each side. Each cross section of the pyramid parallel to the base is a square. Find the volume of the pyramid. Now, when I first looked at this, I set it up completely different than the author of this slide did. So I'm going to show you the way I did it. Actually, their way was easier, but I want to look at it both ways because you might think of it the same way as I did. So here's my xy, and when I think of a pyramid, I think of it sitting on the base. So I'm going to have the base kind of straddle the x-axis. If this is going to be 3 units, we're going to go from negative 1.5 to 1.5. My pyramid will come up here to 3 meters, and my pyramid will look something like this. So each cross section that I'm dealing with is a square, and as these squares get stacked from high to low, I know they don't look like squares now, sorry. These squares will then have a little width, and as I stack these up, I will get my whole volume. So I need to be able to find the point on each square on the middle of the side. So if I draw a line from here, oh dear, well, where'd all my work go? Let's draw my pyramid again, I'm sorry. Oops, hold on. So there's my pyramid. So if I draw a line down the face of the pyramid that connects y equals 3 and x equals 1.5, any point on that line will be halfway through the edge of one of my squares. So the equation of this line is y equals negative 2x plus 3. Slope is down 3 and to the right 1.5. That's a negative 2 slope, and the y-intercept is 3. Now, since I want to find my x value and I'm stacking things up from bottom to top, I'm going to do all of my integration in terms of y, or in respect to dy. So each of these points, if I use my bottom one at 1.5, the area of this base is 2 times x, and then I'm going to square that. So to find my x value on a square that is partway up my pyramid, I need to solve for this equation in terms of x. So y minus 3 divided by negative 2 equals x. If I bring that over here to find my area of my square, 2 times y minus 3 over negative 2 I cross these out, I'm left with a negative 1. So now I have 3 minus y squared. That's the area of 1 square. I'm going to integrate this as I stack my squares from the bottom to the top. I'm going to integrate this from 0 to 3. And I'm going to use dy slices. So my width is a little piece of my y-axis. Okay. So let's keep going with this. I think I left myself a blank page. So I've got the integral from 0 to 3 of 3 minus y squared dy. I'm going to FOIL that. So I've got 9 minus 6y plus y squared. And doing my antiderivative, 9y minus 3y squared plus 1/3 y cubed from 0 to 3. So that's 9 times 3 minus 3 times 9 plus 1/3 times 3 cubed minus, plug in 0, I get a big fat 0. 9 times 3 minus 3 times 9 cancels, and I end up with 1/3 times 3 cubed, which is 3 squared, or 9. So that's the way that I originally thought of doing it. It was a little bit complex because I had to do it in respect to y, and I had to find that x point on that line that I drew. This is what the book did, which I thought was really pretty brilliant. So they drew the pyramid on the with the center going down the x-axis. A typical cross section was here, and they just determined arbitrarily that when I got to x equals 3, my square would be 3 units. So when I'm at x, my square will be x units. So draw the pyramid with its vertex at the origin and its altitude along the interval from 0 to 3. Sketch a typical cross section at any point x, which they've done. So now the cross section of each square is x squared, rather than the formula that I had, which was 3 minus y squared. The limits go from 0 to 3 still, and so their formula came out a bit easier than mine. We still got 9 cubic meters. So take both of those methods, and let's now look at another way that we can do cross sections, and that's with a revolution. So the region between the graph of f of x equals 2 plus x cos x and the x-axis over the interval negative 2 to 2 is revolved around the x-axis to generate a solid. So this is a fairly complex function. If you have a calculator available, it's a good plan to just go ahead and throw it into your calculator to see what it looks like. From negative 2 to 2, the function looked something like this. And since I'm going to rotate this, I'm going to imagine spinning this around the x-axis, and I'll get a whole bunch of little cylinders that are circles. So my cross section is a circle, and it's a full circle, not a semicircle. The radius of this cross section is my function, 2 plus x cos x. And what else do I need? I'm going to integrate it from negative 2 to 2. So from negative 2 to 2, and my cross section will be pi r squared. So I'm going to put the pi out in front, 2 plus x cos x squared dx. This is a perfect candidate for plug and chug into your calculator. If you do so, you should get 52.429 cubic units, or units cubed. Okay, so that one, the setup was pretty straightforward. Our integral was one that was complex enough that that would be a calculator on function. All right, let's look at another one. A solid is made so that its base is the shape of the region between the x-axis and one arch of the curve y equals 2 sine x. Well, y equals sine x I know goes from 0 to pi, so I'm just doing one arch. My amplitude is 2, so there's my sine function. Each cross-section cut perpendicular to the x-axis is a semicircle whose diameter runs from the x-axis to the curve. So that's going to be my diameter from here to here, and it's going to be a semicircle. So I'm going to have a whole bunch of these that are going to make my shape. So I need a couple of things. I need the area of one of these slices. Each slice is going to get a width of dx. That gives me my volume. And I'm going to integrate them from 0 to pi. So the area of a semicircle is 1/2 pi r squared. The radius in this case is the curve of 2 sine x. So I have pi over 2 times 2 sine x squared. Oops, I knew that I missed something there. My radius is not sine x, my radius is 1/2 of sine x. So that looks better. So these 2's will cancel. So I have pi over 2 sine squared x. I'm going to put, again, my pi over 2 outside, and I'm going to put my sine squared x dx inside. We've looked at this several times, and this is one that at this point we need to begin to be able to find or remember what our conversion is. So sine squared x is 1 minus cos of 2x over 2. So I'm going to use that substitution. I'm going to go ahead and bring that 2 outside. Integral from 0 to pi of 1 minus cos 2x dx. So let's do some integration now. We'll go to the next screen. So I'm at this point, pi over 4, integral from 0 to pi of 1 minus cos 2x dx. Pi over 4 times the antiderivative of 1 is x minus sine 2x over 2. If you want to do your u substitution, this is one that I'm fairly comfortable with. If you want to see how I got from here to here using u equals 2x, that's fine. So now, what do I need to do? I need to integrate. I'm good. Pi over 4. So plugging in pi, I get pi minus the sine of 2 pi over 2 minus 0 minus the sine of 0 over 2. Fortunately for me, this is 0, that's 0. I just end up with pi over 4 times pi, which is pi squared over 4, and that is my solution. So we've done a couple where we've had the base of a solid, where we have done cross sections, where we have done a revolution. And that's it for now, and I'll see you in class.